Hello everyone. Today I am going to demonstrate a project Agent Spend and Agent Budget Controller. The problem we are discussing is simple but important. In an enterprise environment, multiple AI agents can continuously make LLM API calls. If these agents are not controlled, a single runaway agent can consume a large portion of team's budget within a very short period of time. The objective of Agent Spend is to provide real-time financial governance for AI agents. I'll first demonstrate how the budget hierarchy is configured. At the top level, we create teams for the demonstration. I'll create various engineering teams with various teams, team name and the budget configured for them. And similarly, we create the agents and the sessions within the team, within that particular team. So next I'll explain about the main execution interface LLM gateway. This is a single entry point through which our agent requests are controlled. So first we select the team, the agents and the session. Now we have configured LLM models. The models are associated through NVIDIA NIM using OpenAI compatible API interfaces. Our primary model is NVIDIA Nematron 3.5 Lightning 30B. This is preferred model for normal executions. We also have NVIDIA Nematron Nano 30B configured as a cheaper fallback model. So routing strategies during the is being straightforward. So when we are having our primary model, we see we'll have a pre-budget analysis. So we'll have a simple prompt being given to the LLM, explain binary search in one paragraph. So before I actually send the request, the system performs a live budget pre-check. The system estimates the expected input, the expected output and calculates the expected cost for the selected model. For example, in this scenario, we have 9 inputs, 400 output tokens and the Lightning model is predicting a cost of 0.35 for this prompt and response generation. So we'll also get the team's sufficient budget, the agent's budget and the session's budget. The important point here is that this happens before the LLM request is executed. So the system is not waiting for the cloud bill at the end of the month. It's making the final financial decision at the request time. So I'll now execute the request. After execution, we record the requested model. The model actually used the input tokens, the output tokens, the total tokens being used, estimated cost and the actual cost, remaining budget and the latency. And then we'll get the LLM responses. So then next we'll demonstrate one important feature of the system, the cost-aware model substitution. So we'll choose a team, the agent and the session by using our primary model Nematron Lightning, and here the pre-checker verdicts us that this particular request is being out of budget and we'll go for a substitution model within the budget. We'll go for a fallback verdict, and this is also being represented in the alert section when we execute it. So during the execution, we see the requested model is not being within the budget, and our model being used is the Nematron 3 Nano 3B 3D, which is not a requested, but we went for a substitution fallback model. And the response for that is being generated. Next, we take a scenario where both primary and the fallback model is being blocked. Yeah. Now I'll demonstrate the case where even the fallback model is unaffordable. The session has no budget rows, and we are requesting that the teams and the agents are being under the budget. So this request is being blocked, and the LLM rejects this before making the LLM call. Next, we'll go for the concurrency demo. Here we have three agents. Here we have three agents: code agent, research agent, and the support agent. I've fired the three agents simultaneously. We can see that all the three agents have submitted the request. The important part is that these requests are happening concurrently, but the budget updates are still handled atomically. This represents multiple agents are raising for the same remaining team budget and accidentally overspeeding. So this demonstrates the concurrency requirement. Multiple agents can request at the same time without breaking the budget constraint. So far, we looked at the financial control. I'll demonstrate now the bonus feature, runaway agent. So as we have fired three concurrent requests, we are starting with the code agent. The code agent has been is operating normally. The system maintains behavioral information such as token uses and requests. By giving a very large input to the code agent, we see that the code agent is being blocked because of the over usage and the sudden spike of the token utilization. Instead of allowing this agent to continue making potential expensive requests, the system automatically pauses it for the review by the manual users. And we also get an alert here that the code agent has been paused due to the runaway agent detection, and the next available agent is the research agent and the session agents. So we'll test whether we can continue with our research and the session agents. So we'll go for select the research agent, and when we are making a request, the budget verdict is within the budget, and we are finally getting our LLM output. So this allows us to understand not just that the agent was passed, but why it was considered risky. And when we are trying to send the request again and again by the same code agent, the LLM doesn't accept these requests, and the requests are blocked because the code agent is being paused for the review. Next is the every health metrics of the agents is being displayed here. The healthy agent can still execute normally, as we saw in the research agent and the support agent. The code agents and one-on-one agents, which is being used for the demo purpose, are being paused and sent for the review because there was a sudden spike usage of the tokens or repeated requests, repeated requests being happening. So in the code agent, we see there are 25 requests being continuously happening, and an increase token utilization in one-on-one, even though the requests are being minimum, but there is a sudden spike of token usages from the other agents. That is why it is being flagged as paused and sent for the review. So this is the runaway agent. And every time the request is being made by the user, everything is being handled and logged in the recent request logger. The request ID, with what agent we are requesting and what model is being used, how many tokens are generated, and what is the cost being handled, and the status of being generation. That is, the code agents are now being in like blocked state, and requesting for permissions, and these research and support agents are being in the completed status, and the time scenarios for generating these. So in the alerts section, as we already discussed, we'll get the substitution alerts being happening from the code agent and the next available agents. So, and also the runaway detectors. And even if we are requesting again and again of the exhausted team, then it will also be alerted to the customer. And these will be marked in a separate incident columns also. So to summarize, Agent Spend provides a complete control layer around LLM execution. Before execution, it estimates the request cost and validates the team agent in session. If the request is affordable, the request executes normally. If it is too expensive, the system attempts a cheaper fallback model. If neither model can fit within the available budget, the request is blocked before execution. So after execution, the actual token usage and the cost are recorded in the logger and maintained in a particular logger page. The system also handles concurrent requests safely through atomic budget reservation. Finally, our runaway agent protection detects abnormal consumption, pauses the problematic agents, and allows healthy agent to continue operating. So the overall goal is not just to track LLM spending after it happens, but to control, explain, and prevent unnecessary LLM spend